Hello and welcome back to Calculus 2, section 7.5, partial fraction decomposition. So in this section we are going to learn a new technique which deals with rational functions when you have polynomial divided by polynomial. No square roots allowed, and clearly none of the previous techniques work, otherwise we would not need the new technique, right? So, yes. What happened?
You labeled the video 7.4.
Oh, yeah, we can't change it. Yeah, okay, thank you. The stream has 7.4 instead of 7.5. Such is luck, right? Thank you for telling me that, but can't change it now. What happened? Yeah, I'll see if I remember. But thank you. So partial fraction decomposition. You might be familiar with the fact that if you have 3x plus 2 plus, let's say, 5 over x minus 3, you can use algebra to add these. So you would have 3x minus 9 plus 5x plus 10 over the common denominator of x plus 2, x minus 3, for the total of 8x plus 1 divided by x plus 2, x minus 3. So what we did here is the basic addition of two rational expressions. You learned this in algebra. We have the answer. Partial fraction decomposition starts here, and it's looking to obtain this form. So partial fraction decomposition is backwards. We start at 8x plus 1 divided by the factors x plus 2, x minus 3, and we are looking for two values, a and b, such that if we do the algebra on them, we'll get 8x plus 1 over x plus 2, x minus 3. So partial fraction decomposition is a procedure which is backwards from adding rational expressions. The way we do this is we add those guys here using the cross multiply. So we have bx plus 2b. Bless you. Okay. So bx plus 2b, why don't I start with b? Ax minus 3a plus bx plus 2b over x plus 2, x minus 3. Note that denominators are the same, so we don't have to worry about those. Right, they cancel. So all I have are numerators now. So I have to consider ax minus 3a plus bx plus 2b equal to 8x plus 1. Note that you have those with x's, and note that you have those without x's. When you combine these with x's, you get that a plus b times x is equal to 8x. And for the other one, you have negative 3a plus 2b is equal to 1. So you write two equations out of one equation. You compare coefficients of x on the left with coefficient of the x on the right, and you compare constant on the left to the constant on the right. So all the purples go on the pile and have their own equation, and all the reds go on the pile and have their own equation. So now, cancel these x's. You have the system. A plus b equals 8. and negative 3a plus 2b equals to 1. Use whatever witchcraft you know to solve the system. Substitution, elimination, matrix, whatever makes you smile. I will multiply the top equation by 3 and then add 2 equations to kill a's. So I have that 5b is equal to 25, from where b is 5. When I feed b's 5 into a plus b equals 8, so I get a plus 5 equals 8, a is immediately 3. Look, a is 3, b is 5. So partial fraction decomposition decomposes these rational functions into addition of these. Now, why do we need this? Well, actually, let me just write this. This is 3 over x, what were those? Plus 2 and x minus 3. So why? Why all of this? Well, integral of 8x plus 1 divided by x squared minus x minus 6 dx can be written as 8x plus 1 divided by x plus 2x minus 3 dx, can be broken into a over x plus 2 plus 5 over x minus 3 dx equals to, insert work here, which is what we did up there, equal to the integral of 3 over x plus 2 plus 5, this was supposed to say b, not 5, 5 over x minus 3 dx, and now you have a basic u subs to give you ln 3 ln of x plus 2 plus 5 ln of x minus 3 plus c. There's no other way to solve this integral. We factor the denominator, we set up the partial fraction decomposition, we solve partial fraction decomposition to get those values, and then from there to here is u sub or basic integrals or whatever pops out of your calculation. So partial fraction decomposition helps you to break this apart. Now, guys, if you're going to differential equations, you are going to need this for inverse Laplace transforms. You have to know this procedure. Otherwise, you will not be able to take inverse Laplace, and that's half of one of the chapters. So you have to learn this. Yes.
I used to ask this, but can you go over the partial part again?
Yeah, we'll do that. When I said insert work here, that's all of this. I did it. This is the same problem. You see the problem? So there it is. And then I set it up with A and B, which is this part. I set it up right here. And then insert work here is the whole thing there. So these problems are a page at best. And then it goes down hill from there. You have to memorize 4 setups. We had 2 linear terms, x plus 2, x minus 3. Great. But we also have repeated and then quadratic. So we remember these 4 setups. If you have something that's blah over x minus c. You know what? Plus minus c, whatever. So this is x plus 2, x minus 5, just x, right? X plus 0. So if you have any of those situations, the setup for partial fraction decomposition is a over x plus minus c. You keep the denominator the same, and you give it a constant on top. If you have the setup that says x plus minus c squared, which is a repeated one, you have a over x plus minus c plus b over x plus minus c squared. If you have irreducible quadratic, so ax squared plus bx plus lowercase c, the setup for that is ax plus b divided by ax squared plus bx plus c. And the last one is the irreducible quadratic repeated. So ax squared plus bx plus c squared, and you should have the same as for the repeated linear. So ax plus b over ax squared plus bx plus c plus cx plus d divided by parenthesis ax squared plus bx plus c, everything squared. Gotta memorize these 4 cases. So what are some features that pop out and help us remember this? First of all, you have a linear squared, quadratic, quadratic squared. Those are the repeated ones. Observe that that's the same with the extra thing, that's the same with the extra thing. The form of these are the same. And also what you see is that the top is always 1 exponent less. X to the first, x to the 0, x to the first, x to the 0, x to the first, x to the 0, x squared, x squared, x squared, x. So always 1 exponent less. So don't let me catch you put a over this. Because, yes?
Where do you find b?
I'm sorry?
Where do you find b to get b on the bottom?
Where would I find b?
Because you have
An alphabet, I guess.
No, but like you have everything up to c in the equation. There's just one b with this.
Oh, these a, b, and c have nothing to do with capital A, B, and c. So you have to compute. You have to compute the system. So if you have a, b, c, we're going to go all the way to, for setup only, not calculation, all the way up to g if you need to, right? Depends on how many of these guys you have. You can have this times that. Then it will be this, and then this will be BC, BE, because you keep using next letters. You can't use, if this is multiplied with that, use A and then use A again, because that would mean it's the same number. It's not, right? So it will be A, B, C, D, E. You can have this times that. A, B, C, D, E, F, G. So we'll see how that works. So first, we practice setup. That's the most important part. Say you have the integral of, observe that I'm not interested in what's in the numerator. So say this is the setup. What do we have? Well, we have 1, 2 linear, and a repeated quadratic. So this is equal to integral. Don't forget the parenthesis, because now we're going into addition. Linear term, a over x, right? You keep the same denominator. Plus another linear, b over x plus 1. That's the setup. Now observe that I'm still using the first formula for the second term, but a is already used up, so I have to use b now. Plus repeated quadratic that cannot be further simplified. So we know it's ax plus b, but a and b are used up, so cx plus d of x squared plus 2 plus ex plus f divided by x squared plus 2 squared dx. This is the setup. So what I have? Linear, linear, repeated quadratic. Linear with a constant on top, another linear with a constant on top, and repeated quadratic is the last formula you have on the list of 4. This used to be A, B, C, D, but A and B are already used up, so you start C, D, E, F. We don't solve this because 1, 2, 3, 4, 5, 6. 6 variables means 6 equations or 6 by 6 matrix, right, to solve this system. So this is just practicing the setup.
Excuse me, ask the question. Cx plus d over x squared plus 2.
That's this. So the last two are these two that are coming from this one, which is this. Let me try to fit them all on the screen. So the last two over here are these two that came from here, which is this. Do we all see that? All right. Let's set up another one. And then do some integrals. Try this one on your own. Ten seconds. 9, 8, 7, 6. Just kidding. So let's take a look. Integral of the first one is a repeated linear. Therefore, a over x plus 3 plus b over x plus 3 squared. That's the setup for the repeated linear. That's the second equation on your list. Plus, this is not repeated, quadratic. Therefore, we just have cx plus d over x squared plus 10 dx. We all have this? Perfect. One more? Real quick? Yeah. So, again, whatever is here, because that does not impact at all our setup. Let's go with x plus 2 squared, and x squared minus 4. I made this even. That's factorable. Oh, damn it. I know. I'm a terrible person. I'm a terrible person. Do we all see the evilness of the question I posed? What's up with that? Yeah, we can factor. Oh, sorry, I didn't mean to put a square over here. Yeah, I didn't mean to put a square there. So this turns out to be, when you factor x and then x plus 2 squared and then x minus 2. You see that? Dx. We can't do it with the cube there. Yes? No, you leave them all separate. So now you have a over x plus, then you have a repeated linear, b over x plus 2, c over x plus 2 squared, plus another linear, d over x minus 2, all of that dx in parentheses. There it is. So when you factor this one, so no square in the original problem, there's no square there. Because I was thinking of it, that I'm going to, have a square eventually, and I put the square there. I didn't want a square there. So when you factor this as x plus 2x minus 2, the x plus 2 and x plus 2 creates a repeated linear. So now you gain a square. And that's why you have to have this as a repeated linear. So you have a single linear, repeated linear, another single linear. That's the setup. Now we go and we solve two examples today. We'll do a few more examples next time. I'm going to pick a few examples from the homework. You guys should read the ones that are already done in a textbook. So let's start with something not too crazy. Problem 14. It's one of the cheaper problems. We have 8 divided by x minus 2x plus 6. So it's already given to you in a factored form. You don't even have to factor. We see 2 linear, so each one of them gets a constant. And now we do partial fraction decomposition. The partial fraction decomposition would be a over x minus 2 plus b over x plus 6 needs to be equal to 8 over x minus 2 x plus 6. We cross multiply on the left. We have ax plus 6a plus bx minus 2b is equal to 8. Remember, we don't have to worry about denominators because denominators will be common, and when you multiply both sides by x squared, x minus 2, x plus 6, they all cancel. So now what do you have? You have, when you collect x terms, you have a plus b times x plus 6a minus 2b equals to 0x plus 8. See, I'm using this 0 as a placeholder for a coefficient of x because I need to compare that. So, comparing these two terms, I know that a plus b is equal to 0. Comparing these two terms, which are constant terms, I know that 6a minus 2b is equal to 8. And now we solve this. Elimination, substitution, matrix, magic beans, whatever works. Times 2 on the top equation, and then add, which gives us 8a, 2b minus 2b is gone, and then equals to 8. A is equal to 1. If a is equal to 1, b must be negative 1, since they have to add to 0. So what you currently see is the partial fraction decomposition piece, which is necessary for us to get a and b, and now we can finally work on the integral. Integral a is 1 divided by x minus 2 minus 1 over x minus 6 or plus 6? Plus 6. This needs to be in parentheses because it needs to be multiplied by dx. Those of you struggling with integration will have to say u equals x minus 2, du equals dx, substitute everything to get into ln. Those of you who know that this integral is already ln, it's ln x minus 2 minus ln x plus 6 plus c. That's the end of the problem. Those of you who are fancy, ln minus ln is the division of arguments. That's another version more compact. Next example is example 30. And then after this, we're going to stop for tonight. So we have dx divided by x cubed minus 2x squared minus 4x plus 8. We have to factor. So what do we factor? We factor out x squared from the first one. We are there with x minus 2. We factor out negative 4 on the second one, and we have x minus 2. Now we factor x minus 2, and we are left with x squared minus 4. But then this one factors into x minus 2, x plus 2, and we see a repeated factor there. So the setup is, don't forget the parenthesis, linear repeated, so a over x minus 2 plus b over x minus 2 squared plus another linear, not repeated, dx. And now partial fraction decomposition. Actually, partial fraction decomposition was earlier. That includes the setup. So what do? I take a over x minus 2 plus b over x minus 2 squared plus c over x plus 2 and equal that to 1 over x minus 2 squared x plus 2. To find common denominator, you don't have to look far. It's already on the right hand side, always. The original problem is always the common denominator. So now you need to play the game of what's missing in each one of these and multiply top and bottom by whatever is missing and multiply through. The rest should be simple. So what am I missing on the first one? I'm missing x minus 2, x plus 2. Because I have two x minus 2's. One is present, I need the other one, and x plus 2. On the next one, I'm missing only x plus 2. And on the third one, both x minus 2's as x plus 2 is present. So these are the things that I have to multiply. Remember that the denominators all cancel because they have common denominator on both sides. So now I have to grind through all of this algebra and put all of the common terms together. When I FOIL x minus 2x plus 2, I get x squared minus 4. So ax squared minus 4a plus bx plus 2b, and now plus this one factored is x squared minus 4x plus 4. So cx squared minus 4cx plus 4c equals to 1. So I'll just say FOIL and FOIL, and then when you multiply by a and multiply by c, you get all of these terms down there. So now what do I have? I have a plus c x squared plus b minus 4c times x plus negative 4a plus 2b plus 4c equals to 0x squared plus 0x plus 1. I put the placeholders in to make sure that I have something to compare for x squared, something to compare for x. So you use the formulas you memorized to come up with the decomposition. And then you equal the decomposition to the original problem, and you have your common denominator, and you say, I have x minus 2, I need another x minus 2 and x plus 2. So I multiply a by those two. I have both x minus 2's, I'm missing x plus 2. And over here I have x plus 2, I'm missing both x minus 2's. FOIL, multiply, distribute, FOIL, multiply, and you get these guys. Combine all x cubes, all x squares on a pile, all x's on a pile, and all constant terms on a pile. So ax squared and cx are the only x squared terms. So a plus c, when you factor out x squared, a plus c. That's the first one. Factor out from px and minus 4cx over there. There they are, the x. And then this one has no x's, this one has no x's, and that one has no x's. They're all together there. Equal to 1. Well, 0x squared, so I can equal this to 0. 0x, so I can equal that to 0. And this is equal to 1. So I am getting now 3 equations from this mess. I'm going to compare this one with the 0. So I have a plus c equals to 0. Going to compare this one with 0, which means b minus 4c equals to 0. And finally the purple, which is negative 4a plus 2b plus 4c equals to 1. Use whatever witchcraft you can to solve this. The cool thing is the top equation is missing b, so times 4 to kill a's when you add it to the last equation. So 4a plus a is gone. 0b plus 2b is 2b. 4c plus 4c is plus 8c is equal to 1. And the equation here is b minus 4c equals to 0. Times 2 on the bottom equation, and then add. So 4b is equal to 1. B is equal to 1/4. One more time, times 2. That's 2b plus 2b is 4b. 8c minus 8c is 0. 0 times 2 is 0. 1 plus 0 is 1. Divide by 4, and we have b is 1/4. So if b is 1/4, right, we have b is 1/4. We can plug that b, because we have that the 4c is equal to b, which is 1/4. So c is equal to 1/16. And if c is equal to 1/16, a has to be negative 1/16 because they have to add to 0. I love these equations because it's always additive inverses there. Solve these equations whatever way you know. Elimination, substitution, matrix, whatever. So now I have my ABC. So what's the integral? It's the integral of a over x minus 2. So a is negative 1/16, 1 over x minus 2. I'm not going to put the fraction on top, just leave it this way. Plus b is 1/4, and we have 1 over x minus 2 squared. plus c 1 over 16 x plus 2. There we go. The first and the last term are easy because that's just a basic ln. The one in the middle, what do I do here? Thank you, basic u sub. U equals x minus 2, du equals dx, and we get integral of 1 over u squared, or du over 1 u squared, which gives us, I hate arrows and I still put arrows, negative 1 over u plus c. All right, so the first integral is negative 1 over 16 ln absolute x minus 2. The next integral is 1/4 times negative 1 over u, so negative 1/4, 1 over, and what's u? U was x minus 2. And the last integral is plus 1 over 16 ln of x plus 2 plus c. How awesome is this? I mean, come on.
Can you explain me again part of the where it says recall? What do you mean?
Where?
Like that. When you recall it.
This?
Yeah.
We have to have common denominator, right? So we have to multiply a by looking at this denominator here and looking at the denominator on the other side. We have to multiply with everything that it's missing.
Okay.
So when you FOIL this,
Will
you
you
multiply.
what is missing a?
Well, you look at the denominator and you look at the denominator, you compare, you see what's missing, and that's what we're multiplying by. So x minus 2. This over here is x minus 2, x minus 2, x plus 2. So you see that we already have one, we need the other two, and that's why I have them up there in purple. It's the same, each term works the same way. And then you distribute all A's, B's, and C's to get the long string. It will take, yeah, it will take time. Yes, it will take time if you haven't seen, because we teach this in our PreCalculus 1 course. We teach this technique. We don't teach integrals or anything like that. We teach this in our PreCalculus courses, so students who took PreCalculus here at RV, they know this already. So half of the classroom probably already knows this procedure, what you see on a screen, and we are adding now the integral part on the bottom. All right, so we'll do more examples of this next class.
See you Monday.
Yeah, yep.